And now in this lecture we'll find out the area of rectangle ABCD. In the drawing we have rectangle ABCD. Inside this rectangle we have this semicircle. Note that this is line segment AP, that is equals to 6 units in its length. This is line segment PC, that is equal to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So first of all, we know that all the angles inside the rectangle are right angles. So this is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. In the next step, we define the center of this semicircle. This point is point O. We will define the touching point of this semicircle with side AB of this rectangle ABCD. This point is point E. And finally, we will define the point of tendency or tangent DC with this semicircle. This point is point M. In the next step, we will join points O and M together by a straight line. Point O is the center of this semicircle. Point M is the point on the semicircle itself. Therefore, OM is the radius of this semicircle. We will define the radius of this semicircle as x. So OM equals to x is the radius of this semicircle. So the radius of the semicircle is equal to x units according to our definition. Point O is the center of this semicircle. Point A is the point on the semicircle itself. Therefore, OA is also the radius of this semicircle, that is equal to x. Likewise, OE is also the radius of this semicircle, that is equal to x units in its length. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. In the drawing, we have a circle, and this is tangent AB, that is tangent to this circle, and this point M. Point M is the point of tendency of tangent AB with this circle, and we also have the radius OM that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule 1. So we can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius OM that is equals to x. The radius OM is drawn to point M, that is the point of tendency of tangent DC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside the quadrilateral MCBO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4th missing angle, in total they must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4th missing angle must be equal to 90 degrees in its size. So inside quadrilateral OMCB, inside this quadrilateral, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle plus a square. So we write to this quadrilateral OMCB that has 4 right angles as a rectangle because it has 4 right angles. Okay. But we also know that the opposite sides of a rectangle are equal to each other. So in this rectangle OMCB, side OM must be equal to the opposite side CB, but OM is x, therefore CB must be also equal to x units in its length. We will join, in the next step, we will join points P and E together by straight line. By joining points P and E, we created this peripheral angle EPA. This peripheral angle EPA subtends on AE, that is the diameter of this semicircle, and we know that any peripheral angle that subtends on the diameter of the circle or semicircle, it is equal to 90 degrees in its size. So this is according to rule 5. So repeat quickly, actually it is according to rule 7. So repeat quickly rule 7. If a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees. In the drawing we have a circle. AB is the diameter of this circle. And this is peripheral angle CB that subtends on AB, that is the diameter of this circle. And whenever you have a peripheral angle that subtends on the diameter of the circle, then it is equal to 90 degrees in its size. Therefore, peripheral angle CB is a right angle. Okay? So we can actually implement rule 7 in our drawing. Why? Because in our drawing, this is peripheral angle APE that subtends on AE, that is the diameter of this semicircle, and therefore, according to rule 7, it is equal to 90 degrees in its size. In the next step, we will focus on this triangle APE. We will define this angle as alpha. So in the right triangle APE, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we will focus on the big right triangle ABC. This big triangle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this missing angle must be equal to 90 degrees minus alpha. According to the same rule, that the sum of the angles in any triangle is equal to 180 degrees. So, in the next step, actually, this angle is a common angle that belongs to both triangles. It belongs to the big triangle ABC, and this angle belongs also to triangle APE. So this angle A is a common angle that belongs to both triangles. So in the next step, we will prove that the big triangle ABC is similar to this triangle APE. Okay. Triangle ABC is similar to this triangle APE. So, why those two right triangles are similar to each other? First of all, this is angle A, that is a common angle that belongs to both triangles. So we can write down that angle A equals to itself is a common angle that belongs to both triangles. So if we relate to this angle, angle A, since it belongs to the big triangle ABC, it will be defined as angle CAB. And angle A equals to itself. So if we relate to this angle A, as it belongs to triangle PEC, it will be defined as angle PAE. So this equation means that angle A equals to itself. We just call to angle A two different names. Angle A equals to itself. It's a common angle that belongs to both triangles. This is angle CBA in triangle ABC. That is equal to this angle, angle EPA in triangle APE. They are both equal to 90 degrees and therefore they are equal to each other. Repeat again. Angle CBA in the big triangle ABC is equal to angle EPA in the right triangle APA. They are both equal to 90 degrees and therefore they are equal to each other. And finally, this is angle ACB. In the right triangle, triangle ABC, and it is equal to this angle. This is actually angle PEA in triangle EPA. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. Repeat again. Angle ACB in triangle ABC is equal to angle PEA in triangle APA. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually proved that all the three angles of the right triangle ABC are correspondingly equal to all the three angles of the right triangle, triangle APA. Therefore, those two triangles are similar to each other according to angle similarity rule. So I write it down. Donc we found out that the big triangle ABC, the big right triangle ABC is similar, this is the sign of similar, to the right triangle, triangle APE according to angle similarity rule. And for the fact that the big right triangle ABC is similar to the right triangle APA, we will derive that the following relationship exists between their sides. We will derive that side AP of triangle APE over side AB of the right big triangle ABC is equal to side AE of triangle APE over side AC of the right big triangle, triangle ABC. Repeat again. From the fact that triangle APE is similar to the big triangle ABC, we derive that the following relationship exists between their sides. We derive that side AP of the right triangle APE over side AB of the right big triangle ABC is equal to side AE of triangle APE over side AC of the big right triangle, triangle ABC. AP equals to 6 units in itself, according to what is given as the question, over AB. AB is the missing side, so we will leave it as it is. And it is equal to AE. AE equals to x plus x, that is 2x. This is actually the diameter of the semicircle. So So A equals to 2x over AC. AC in total equals to 6 plus 5, that is 11. AC equals to 11 units in incident. So we have found out that 6 over AB equals to 2x over 11. Here we will cross multiply this equation and we get that 6 times 11, that is 66, is equal to 2x times AB. After we cross multiply this equation, we found out that 66 equals to 2x times AB. Here we will divide this equation by 2 and we get that 66 over 2 is 33, is equal to x times AB. So here we will divide this equation by x. It is allowable to divide the equation by x because x is the radius of this circle, so it can never be equal to 0. Therefore it is allowable to divide this equation by x. It must be a positive number. So here we get that AB equals to 33 over x. So if you found out that the length of this side AB of rectangle ABCD is equal to 33 over x. AB is the length of rectangle ABCD and CB is the width of rectangle ABCD. We know that the area of any rectangle is equal to the length of the rectangle times the width. This is the area of a rectangle. So we are looking for the area of rectangle ABCD. And we know that the area of a rectangle is equal to the length of the rectangle times the width. And therefore the area of this rectangle ABCD must be equal to the length of the rectangle of this rectangle ABCD times the width. The length of this rectangle ABCD is AB times the width. The width is CB, that is x. The width is CB. But we already found out that the length AB is 33 over x, and we have to multiply the length by the width. The width is CB, that is x. So in total we found out that the area of rectangle ABCD equals to 33 over x times x. So here we have x in the numerator and x in the denominator, so x will get cancelled. And we left only with 33 square units. So we actually found out that the area of this rectangle ABCD is equal to 33 square units. So in the next step, I will summarize the lecture. So our mission in this lecture is to find out the area of this rectangle ABCD. Inside this rectangle we have this semicircle, and we know that this is line segment AP, that is equal to 6 units in its length. This is line segment PC, that is equal to 5 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So first of all, because of the fact that ABCD is a rectangle, all its 4 angles, those 4 angles are all right angles. The next step, we define the center of this semicircle. This point is point O. We define the touching point of this semicircle with side AB of rectangle ABCD. This point is point E. And we define the point of tendency of this semicircle with side DC of rectangle ABCD. This point is point M. We define the radius of this semicircle as x. In the next step, we join points O and M together by a straight line. Point O is the center of the semicircle, point M is the point on the semicircle itself, therefore OM is the radius of this semicircle that is equal to x units in itself according to our definition. And because of the fact that the radius OM that is equal to x, the radius OM is drawn to point M, that is the point of tendency of tangent DC if this semicircle, and whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If this is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So actually, in this quadrangle MCBO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside this quadrangle MCBO, we have 4 right angles, and according to rule 5, any quadrangle that has 4 right angles must be this rectangle if not a square. So we relate to this quadrangle MCBO as a rectangle because it has 4 right angles. But we also know that the opposite sides of the rectangle are equal to each other. So in rectangle MCBO, side OM must be equal to the opposite side BC. But OM is x, it is the radius of this circle that is x. Therefore, the opposite side BC must be also equal to x units in its length. In the next step, we join points P and A together by straight line. So by doing this construction, you can do here peripheral angle EPA. This is peripheral angle EPA. This is peripheral angle EPA that subtends on AE, that is the diameter of this semicircle. And according to rule 7, any peripheral angle that subtends on the diameter of the circle or semicircle must be equal to 90 degrees in its size. Therefore, this angle is equal to 90 degrees in its size. So, I'll repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees. So in the domain, we have a circle. AB is the diameter of this circle because it passes through point O, that is the center of this circle. And we have here peripheral angle ACB that subtends on AB, that is the diameter of this circle, and because of the fact that peripheral angle ACB subtends on the diameter of this circle, it must be equal to 90 degrees in its size. Therefore, this peripheral angle equals to 90 degrees in its size. So we can actually implement rule 7 in our drawing. Why? Because of the fact that this is peripheral angle APE that subtends on AE, that is the diameter of this semicircle. Therefore, this peripheral angle APE must be equal to 90 degrees in its size according to rule 7. In the next step, so we have here triangle APE, the right triangle APE. We define this angle as alpha. So in the right triangle APE, this angle equals to alpha, this angle equals to 90 degrees minus alpha, and this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on this big right triangle ABC. In this big triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha according to the same rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that this big right triangle ABC is similar to this right triangle, triangle AP. So why those two right triangles are similar to each other? First of all, this is angle A, that is a common angle that belongs to both triangles. So you can write down that angle A equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we prove that all the three angles of this big right triangle ABC are correspondingly equal to all the three angles of this triangle APE, the right triangle APE, therefore those two right triangles are similar to each other according to angle similarity rule. Repeat again. Triangle ABC is similar, this is the sign of similar, to the right triangle APE according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the right triangle APE over side AB of the right big triangle ABC is equal to side AE of the right triangle APE over side AC of the right big triangle ABC. Repeat again. We will derive that side AP of triangle APE over side AB of the right big triangle ABC is equal to side AE of triangle APE over side AC of the right big triangle ABC. AP is 6 according to what is given as the question. AB is the missing side, so we leave it as it is, and it is equal to AE. AE is the diameter of this semicircle that is equal to x plus x, that is 2x. So A equals to 2x, and AC, this is side AC, that in total it is equal to 6 plus 5, that is 11. So AC equals to 11. AC equals to 11. So in total, we actually found out that 6 over 11 equals to 2x. 6 over AB equals to 2x over 11. Here we cross multiply this equation. We actually found out that 6 times 11 is 66. And it is equal to 2x times AB. So 66 equals to 2x times AB. Here we divided this equation by 2 and found out that 66 over 2 is 33. So 33 equals to x times AB. Here we divided this equation by x and finally found out that AB equals to 33 over x. So AB is the length of this rectangle ABC that is equal to 33 over x units in its length. Our mission is to find out the area of this rectangle ABCD. We have to find out the area of rectangle ABCD. Actually, we know that the area of any rectangle equals to the length of the rectangle times the width. The length of this rectangle ABCD is AB, and the width is CB. The length is AB, and the width is CB. So it is AB times CB. But we have already found out that AB equals to 33 over x. So we substitute AB by 33 over x times CB. We already found out that CB equals to x units in its length. So we substitute CB by x. So in total we actually found out that the area of rectangle ABCD equals to 33 over x times x. We have x in the numerator and x in the denominator, so x will get cancelled, and we left only with 33. So we actually found out that the area of this rectangle ABCD is equal to 33 square units. Okay, thank you very much.